So today I'll be doing a presentation on an independent study that I've been doing for the past semester on computer vision and autonomous navigation. And the reason why I'm presenting it all to you here is because that is what I was doing for the entirety of this robotics season. So, some of you, cough programming team members, probably know some of this, cough Ben.
That's me.
Yep. But anyway, so those sheets right there, okay, you already got the writing utensils. If you could just fill those out, give them back to me sometime before you leave, that would be great, just so I, know how I did, that sort of thing. But, so now with that out of the way, let's get started. So, first, a little bit about me, for those of you who don't know me already. So, I'm planning on going into either computer engineering or electrical engineering, haven't quite decided on one. I've been on this team for 3 years, those of you who haven't been here for 3 years, and I was programming lead this year, which is why I did that. And I was pseudo manipulator lead last year and did some other stuff my freshman year. So just a little bit of that. But now, so the things I wanted to do during my independent studies, so I wanted to figure out, so how does a computer vision system recognize targets? So those, for example, in our case would be the vision targets on the field. And how does a navigation system plan a path? How does the robot get to its destination by itself? And how can you combine those two systems together to make something that works? So now a little bit of obligatory paperwork here. So during the independent study, I wrote a variety of reports, which you can see in here after the presentation is done. So the first one was on a little amplifier circuit that I built at the beginning of the independent study, but then I changed topics, but it still counts. So then I have the computer vision APA paper with it, which was just a research paper on the topic of computer vision and common techniques used for it. And the computer vision system overview was an overview of the vision system on the robot. And then the navigation system overview was an overview of the navigation system on the robot. All right, so now into the actual interesting bits. So the goal, or at least the goal for our team, was get these game pieces onto the field. Except we wanted to do it better than James could. So we decided that we should try using an autonomous system. One that used these vision targets right here to line up to the target and place the object. So that was the idea. Now, when I say computer vision, I've been saying it this whole time, what exactly do I mean by computer vision? So, it's not that. But what a computer vision system actually is any computer system that gets data out of an image. So that can be recognizing the object in an image, or classifying all the objects in an image. That's useful for things like, self-driving cars, industrial robots, or for placing game pieces on a field on a robotics competition. So now, how does all that work? Well, first of all, so we have our vision target here, right? And what we want to know is there a target in this image, or is there not? If there is a target in the image, where is it relative to the camera? So that's what we want to know. So first, we shine a very bright light at it, at the targets, and the tape is reflective. So if you see something that's bright and green, then you know that's your target. Now, the thing is, you run into a minor problem if you just try to put a camera on a robot and have it look at the image. So with an image like this, you can see it's very faded out, mostly white. That's because of overexposure. So that's when sensors in the camera get filled up too much, and they saturate at white, and they can't go any brighter. So that's when too much light enters the camera. So first you have to set the exposure of the camera very low so it doesn't do that. So then you end up with an image like this. And yes, I realize this is Stronghold's vision target, but we're not going to say that. So now you have an image like this, where you have your object, which is green, and there's your target. So you want to recognize that. Okay, well, how do you do that? Well, figure out what's green in the image. If something is green, it's a target. Easy enough. But the problem is, most images are represented with RGB color. So that's the amount of red, the amount of green, and the amount of blue light in each pixel. And as it turns out, using that to detect whether or not a pixel is green is actually quite difficult, because you have to account for ratios of the different colors, and it's just really not a fun time. So what you do instead is you convert all the pixels to what's called HSV first, which represents the, see, I see you're smiling, of course, which basically just represents it instead with the color of the pixel, the brightness of the pixel, and the intensity of the color. So then you can just check, okay, is it between here and here? If it is, then it's green. Done. No questions asked. That's all you have to do. So first you do that, then you check whether all the pixels are green. And you start with this, and then after you check, you end up with that. So all the white pixels are the ones that were found as green. All the black ones were ones that were not green. Then, what we did is we applied what's called a closing, also lots of fun there. So just, it removes all the little small imperfections in the middle of the shape. You get yourself a nice smooth shape like the one on the right, because these will mess up all your other algorithms. So then all we have to do is find the contour of the target. So we draw a box around the shape, and we say, okay, well, does it have 4 sides? Because if it doesn't have 4 sides, then then that's wrong. So first we check that. Then you can check a variety of other things, like how much of this box is actually filled in, because that will also tell you whether or not your target is right. And there's a variety of other techniques you can use to figure out whether something is a target or not. And once you've done all of that, and you know that it is a target, you just pick the center of the box, and then you do some math on it with the field of view of the camera and the height of the target, and then you figure out angle of the target and the distance of the target from the robot. And we did that successfully. So now that you know where the target is, how do you get there? Well, the thing is, so we use the differential drive robot. Cameron. Okay, so with a differential drive robot, if you put both sides, we have 2 things we can control: the speed of the wheels on the left and the speed of the wheels on the right, right? So if you put both of them at the same speed, robot drives in a straight line. If you put both of them at different speeds, you have the robot move in an arc, and the radius of that arc is dependent on the difference between the wheel speeds. So robot moves in either straight lines or circles. All right, pretty simple. Now, this is not fun, but I can tell you that what is happening here is you can find the position and the angle of the robot at any time if you know the speeds of the wheels, which makes sense. If you drive forward at this speed for this long, you should know where you are. Now, the thing is, what we want to do is the reverse. If we know where we want to go, how do we get the wheel speeds to get there? And that problem is actually very hard, because the angle of the robot affects where it can move. So our robot can't drive sideways. It can only drive forwards or backwards, and it can turn. So if you had a swerve drive robot, you could go go wherever you wanted with no problems at any time. With our robot, you can't. So these sorts of problems are called holonomic problems, and that means they follow a certain form and they're really easy to find equations to solve. This type of problem, where the way the robot can move depends on the way it is facing, is non-holonomic, which means it's very difficult to solve. So the calculations, if our robot was a swerve drive robot, to get to a target, look like this. We don't get to have that. The calculations for our robot look like that. That is not a fun curve to calculate. I can tell you that from experience. So there's actually, from the research I did, it appeared that there was no perfect solution for finding a path like that, because all of them were limited in some way by speed or resolution or number of points or something like that. So what we did instead is we used a small approximation, which was turn towards the target, drive to the target, and then turn to face the correct direction. And that's how we did it. And that worked relatively well. So then, all you had to do to combine those two together was you take the output of the computer vision system. Okay, this is where my target is. And you plug that into the navigation system. Okay, now go there. And there you go. Now you have a computer vision and navigation system. And that's what we did for 6 weeks. So now the benefits of such a system are many. So you get reliability, you get speed, you get accuracy, and you get bragging rights. Because saying your robot does everything by itself is much cooler than having someone drive it. No offense, James. But, so there's a variety of other benefits that I won't go over here, but suffice it to say that autonomous systems are, as a rule of thumb, just better than human systems, because computers don't really make mistakes. James does. So now that we've gone over that, so what we plan to do next year is, we didn't get to use this system on our robot during competition, much to our dismay, but and James's enjoyment. But what we plan to do next year is fine-tune the system so it can be faster and it can be accurate enough to work. Because while I did say, yes, they're more reliable and faster and more accurate, it requires some work to get to that point. And we just didn't have enough time to get it to a point where it would work well enough for our purposes. So next year we're going to do that. Next year we're also going to make some changes and improvements to the system, like, so when the camera captures an image, that's great, except when it actually gets to the calculations, the image is now an image from like 50 milliseconds ago. So your robot thinks the target is here, except it's moved since then. So it thinks it's here, which means your robot is going to try to go here instead of here, which is bad and can lead to things like oscillations, where your robot just turns to the left and the right repeatedly, and that's not fun. So you can compensate for that by saying, okay, well, where's the camera relative to where I was 50 milliseconds ago when the image was actually taken? So you can do that sort of thing. And overall, I would say for a first attempt at a vision system, computer vision and navigation system, it went fairly well, and I think it has promise for future years. So, any questions?
So you're not going to make a camera do this work good?